Today we're going to talk about the law of cosines, which is another trig tool for us. But this trig tool can be used for any triangle, not necessarily just a right triangle. Yesterday we learned the law of sines, and that's a very useful tool for us, but it does have some pitfalls in it that we need to be aware of, and that's where the law of cosines is going to come in. So a little bit of review. If we have a triangle, there are some tools that come into play. One of them is that the sum of the interior angles, which we're calling alpha, beta, and gamma, but they could be any three variables, the sum of those three angles needs to be equivalent to 180. The second tool that we developed yesterday was the law of sines, which said the sine of the angle opposite A, or what we're calling alpha, divided by A would be equivalent to the sine of beta over B, which would also be equivalent to the sine of gamma over C. The new tool that we're going to learn today is the law of cosines. And the law of cosines, unfortunately, is a little bit more complex. But it says a squared equals b squared plus c squared. It looks a lot like the Pythagorean theorem. Minus 2bc cosine of alpha. Notice that alpha is the angle that is opposite of the a. So these two are corresponding, as well as the b corresponding and the c corresponding. There are two other versions of this same law of cosines. One starts with a b squared, and we get a squared plus c squared. This would now be minus 2ac, and now we would have the cosine of the angle opposite b, which is beta. The final version, c squared equals a squared plus b squared minus the 2ab, cosine of the angle opposite of c, which is gamma. All three of these work. It just depends on what we have and what we're looking for. If we have angle beta, we would need to use the second iteration of the law of cosines. If we had all of A, B, and C and we're looking for an angle, then we're going to have to choose which of these three we'd like to use. A bit more of review. If we have two angles given to us, angle, angle, side, or angle, side, angle, the best tool here is going to be the law of sines. This is a great tool for us if we're given two angles. Another possibility is we're given two sides and the non-included angle. This was our ambiguous scenario where we could have no triangle, we could have one triangle, or we could have two triangles. Both laws here are good for us, but we need to be smart about the ambiguous scenario. Some more scenarios would be if we're given all three sides, or we're given two sides and the included angle. In this case, we can't use the law of sines. We would have to at least start with the law of cosines before moving towards the law of sines. The final scenario is, what if we're given all three angles? Well, if we're given all three angles, we cannot determine the length of those legs, so this would be inconclusive. There would not be enough information there to be able to determine or solve the triangle. Gamma is going to be 20 degrees. We do know A to be 11. We do know B is going to be 5. And we do not know C. So we're going to solve for those three missing values. It's going to be important to recognize, do we have multiple angles? In this case, we do not, so we're not going to use the law of sines right off the bat. We have, in this case, side, angle, side. We have two sides, A and B, and then we have the included angle between A and B, which is 20 degrees. For this, I'm going to use the law of cosines. In particular, I'm going to use the third iteration where we have gamma involved. So my first calculation would be that c squared would have to equal a squared plus b squared minus 2ab cosine of gamma. I can plug in for three of the four unknowns. The only unknown is going to be c. When I plug in here and solve, I can isolate my c by determining the value on the right side and taking the square root. I get a c value there of approximately 6.529. At this point, I can now determine the other two angles using the law of sines, or the sum of the interior angles equaling 180. A big red flag for us here is the law of sines is going to fail us when we are looking for an obtuse angle. So we do not want to use for obtuse angles. That speaks to the domain and range of the inverse sine function. We don't have the inverse sine function memorized, the graph of that, but we cannot use the law of sines to determine obtuse angles. So of these two missing angles, which is the one that could be obtuse? Well, opposite the 11, that might be obtuse. So I'm not going to use the law of sines to determine alpha. I can use the law of sines to determine beta though. So I'll say the sine of beta over 5 equals the sine of 20 degrees over what I just found for C. I'd like to reference that exactly. I can cross multiply and take the inverse sine of 5 times the sine of 20 degrees divided by the exact value of C. Try not to use a rounded value there. I get a B of 15.183 degrees. I can then use the sum of interior angles equaling 180 to find my alpha. I do 180 minus the 20 minus the 15 and change, and I get 144.817 degrees. Important note there, that alpha is an obtuse angle. So if I had used, instead of the sine of beta over b, if I had used the sine of alpha over 11 and tried to determine alpha right away, I would have gotten an incorrect answer. That's something we can explore more in class tomorrow. The second question I'm going to go through here, again, we're going to be given a triangle, and for this triangle, we're not going to be given any angles. So we don't know alpha, beta, or gamma. These are all unknown to us. We will know that A is equal to 9, B is equal to 7, and C is equal to 5. This would be our side, side, side scenario. Because this is side, 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 I have to at least start with the law of cosines. For this, because the law of cosines will be better with obtuse angles, I'm going to start by trying to find alpha. Opposite of the largest side would be the largest angle. If that's obtuse, the law of cosines is what's going to get it done for me. So I'm going to start with the iteration that says a squared equals b squared plus c squared minus 2bc, the cosine of alpha. 9 squared equals 7 squared plus 5 squared minus 2 times 7 times 5, cosine of alpha. This is going to require some work on our part. We're going to have 81 minus 49 minus 25, which is going to give us 7, equals negative 70 cosine of alpha. Divide the negative 70 over, we get negative 0.1 cosine of alpha. To determine alpha, we would do the inverse cosine of negative 0.1. Make sure when we're degree mode here, we would get an alpha value of 95.739. We see an obtuse angle. We're grateful that we did the law of cosines there. We can now move to the law of sines because neither of the angles remaining could possibly be obtuse. The sine of that 95.739 divided by 9 equals the sine of beta over 7. Beta would equal the inverse sine of 7 times the sine of alpha over 9. Here I'll get a rounded decimal 50.704. I can use the fact that all three angles need to add up to 180, or I could use the law of sines to confirm here, but I'll get 33.557 degrees. I'm going to leave you with 4 examples to check out today. Think about what is given here. Are we given 2 angles and a side? Are we given 2 sides and an angle? If so, what order are we in? Are we given all 3 sides? Are we given all 3 angles? What tool is going to be best to start with? What is necessary to find the correct solutions? Good luck.